So, hello everyone, and welcome back to my channel. Today we are at day 20 of the April Daily Code Challenge, and we have a medium level question in front of us. Let us see what the question is. It's question 662. Okay, maximum width of a binary tree. So, what we're given is we are given a root of a binary tree, and we have written the maximum width possible. Okay, maximum width possible for the given tree. It's clearly mentioned the maximum width of a tree is maximum width along all the levels. Okay, first of all, let us understand what the level is. Okay, so you can clearly see level means a distance from root. Okay, for example, if we consider the 2 and 3 these nodes, they are level distance 1 from the root. Okay, so they are called level 1 nodes. Okay, similarly the root is at level 0. Similarly, if you consider the leaf nodes here, they are at level 2. Okay, that is how it is being done. So level basically means the distance from the root. Okay, so now let us understand what the question is. So we have to find the maximum width of the tree, that is maximum width among all the levels. Okay, among all the levels. This is very, very important. Please note this point down. Among all the levels. Okay. So now we are going to the definition of what a width is. Width of one level is defined as the length between the end nodes. Okay. See, this point is very, very important. Leftmost and rightmost not null nodes. Okay. That is the width, the definition of width, and we have written the maximum width. Okay. Let us see some examples. At level 0, you can clearly see there is only one node. Okay. So the width in this case will be 1. So by the way, what is the formula for finding width? Width will be the index. Okay, I will say you as we see the examples. So yeah, coming to the level 1, you can clearly see that they are here. Only two nodes are here. Okay, so the distance among them, so the width will be 2. Now coming to this, the level 3, you can clearly see 5 is here, 3 is here. So one more node will come from 2, right? One more child will come from 2. That also we have to count, and then 9. So total 1, 2, 3, and 4, because see, these are mentioning where the null nodes between the end nodes that would be present in a complete binary extending down. Yeah, see, we have to consider that as well. Okay, we have to consider the null nodes between the not null nodes. Okay, so that means one child will come from for 2. That also we need to consider. So you can see finally we will have 5, 3, one child coming from 2, and finally 9. So total 4 nodes in the level 2. Okay, in the level 2. So that's why the answer is 4. Okay, this is the one. 5, 3, null, and 9. Okay, they are calling the child coming from 2 as null. Okay, so the maximum width coming in this case is at level 2. At level 1, we had width of 1, width of 2, and the level 0, we have width of 1. Okay, now coming to this example, see, you have to be very, very clear what we are doing here, otherwise it will be very difficult for you to understand. Okay, see, we can clearly see the level at the level 1, the width is 2. At level 2, the width will be 4. We all know that. But at level 3, when we talk about level 3, we have to consider the leftmost and rightmost not null nodes. Okay, the leftmost not null node is 6, and the rightmost not null node is 7. See, the other child of null will not be considered here because we have to consider the width between the leftmost and the rightmost not null nodes. Okay, so we will not consider the right child of 9. We only will consider the left child till the left child of 9, from 6 till the left child of 9. Okay, so now let us trace it. One right child will come for 3. Okay, at level 2, one right child will come for 3, and similarly one left child will come for 2. Okay, one right child will come for 3, one left child will come for 2. They will have two children at the level 3. Okay, they will have two children at the level 3. Okay, so just to count 2 plus 2, 4. One child will come from 5, so 4 plus 1, 5, and 6 and 7. Okay, I will again do. See, please be very, just try to trace the mouse pointer. Okay, one child will come for 3. Okay, and the level 2. Similarly, one child will come from level 2 in the level 2. So this will have one child, this will have one child in the level 2. Okay, this is my level 2. Okay, see the mouse pointer. Now that particular child will have two nodes in the level 3. So overall, so two nodes will come from this particular thing. Okay, the right child of 3 will contribute two nodes in level 3. So count 2. Similarly, the left child of 2 will contribute two nodes in level 3. So 2 plus 2, 4. Okay, 5 will the right child of 5 will contribute one node. So 4 plus 1, 5. Okay, 5. And now 6, these two are also there. These 6 and 7 which you are seeing here, that also have to add. So 5 plus 1 plus 1, which is 7. You can clearly see the answer is 7. Okay. See, this is the right child of 5. Okay, these two are coming from node 3, the right child of node 3. Okay, these two are coming from left child of node 2. Okay, and this is the seventh node. Okay, this we are talking about. Okay, this is the sixth node which we are seeing here. So total, if you calculate the length of this, okay, this is around 7. Okay, around 7. So now see, this example is very, very important for you to understand the edge cases. Okay, in the question is clearly given the definition of width is, yeah, the distance that means the length between the end nodes, that is leftmost and rightmost not null node. So at least two nodes should be there. One is the one will be called the leftmost, and the other will act as a rightmost not null node. Okay. In this question, you can clearly see the level 2 do not have a rightmost node. There is only a leftmost node. There is no rightmost node. Okay. So both leftmost and rightmost will be the same in this case. Okay. So the width will be 1 along the level 2. Coming to level 1, the width will be 2 because there are two nodes present, so it will be 2. Along level 2, width will be 1, okay, because there is only one node. Similarly, for level 0, the width will be 1. So you can clearly see the maximum width is coming at level 1, okay. So 2 comma 3, sorry, 3 comma 2, in the level 1, we will contribute for the maximum width, which is 2, okay. Width is basically, see, I hope you will be understanding now what is width. Okay, width is basically, see, at any level, consider the leftmost and the rightmost not null node, okay. Once you have considered them, the nodes which are coming in between them, even if they do not exist, you have to consider them. See, only the leftmost and the rightmost node should be not null. Any node in between them, even if it doesn't exist, then also you have to consider them. That means you have to consider the null nodes also. That is the basic idea. That's what we are seeing here, right? See, the descendant of 5 is not here, okay? The right node of 5 is not here. Similarly, the right node of 3 and its children are not here, but still we have to consider them to calculate the width, okay? So had it been some children here, so what would be the width? That's what we have to consider. Now coming to my solution. So this is my solution. I'm using the deface approach. This is my deface function. I'm calling it from the root. Okay, I'm using a data structure dictionary. A is a dictionary. So in A, I'll show the leftmost and the rightmost not null nodes. Okay. So see, in my example, I will quickly show you what I'm doing. The first node, I'm calling it as index 0. Then its children, see, this is what I'm following. The leftmost node, see, suppose my current root is I. Its left child will be 2i plus 1 index, okay? Similarly, its right child will be 2i plus 2 index, okay? This is actually what we do in a heap. I will just use this technique here. So please be mindful of, please pay attention. You will definitely understand what I'm saying, okay? If my root is I, okay? If my root is I, its left child will be 2i plus 1, okay? And the right child will be 2i plus 2. Let us see how. See, I can't write and show you, but please pay attention. I'm sure you will understand, okay? 1 is 0, okay? Its child will be 2i plus 1 and 2i plus 2. Just do, if I equal to 0, what is 2i plus 1 and 2i plus 2? You will get 1 and 2. So its child have 1 and 2, okay? 0, 1, 2. Now this will be 3 and 4, okay? When I equal to 1, just do 2i plus 1 and 2i plus 2. You will get 0, 1, 2. 3 and 4, okay? You will get 3 and 4. Similarly, for 2, 0, 1, 2. If you do 2i plus 1 and 2i plus 2, what you will get? So this 0, 1, 2, 3, 4, 5 and 6 you will get, okay? When I equal to 2, you will get 5 and 6. 2i plus 1, 2i plus 2. So 0, 1, 2, 3, 4, 1 will come here, 5, 6, okay? That's how we are doing the naming, okay? For example, if we try this, okay, I will just try and show you how it works. So here it is, see, at level 0, the leftmost node is also 0, the rightmost node is also 0, okay? This we are talking about example 1, okay? Coming to the level 1, okay, 0, so its shall be 1 and 2, okay. So you can see there are only two nodes present, so they are 1 and 2. So leftmost northern node is 1, the rightmost northern node is 2, okay. Now coming to level 2, see 0, 1, 2, 3, 4, 5, 6, okay. So it's starting from 3, the leftmost northern node is 3, and the rightmost node is 6. This numbering I'm doing so that I can get the final width, okay. What is the width? Width will be 6 minus 3 plus 1, okay. It will be 6 minus 3 plus 1. Now coming to second example, see, width as this node is both leftmost and rightmost are the same node, so 0 the index, okay. So it will be the same. Coming to level 1, it is index 1 and 2. See, root is index 0, so its child will be 2i plus 1 and 2i plus 2, where I equal to 0. So it will be 1 comma 2, right? Same here, it is written 1 comma 2. Okay. Now coming to this, see 0, 1, 2, 3, 4, 5, and 6. Okay. So starting from 3 and you get 6. Okay. 3, 4, 5, and 6. Okay. Then comes 7, 8, 9, 10, 11, 12, 13. Okay. See, this sixth node which you're seeing is has an index of 7. I will show you how. See, 0, just follow the mouse pointer. 0, 1, 2, 3, 4, 5, 6, 7. Okay. It has an index of 7, 8, okay, 9, 10, and then from here 11, 12, and then 7 is 13. So leftmost Norton node is 7, rightmost Norton node is 13. I'm counting scene. These things I've already explained, that's why I'm not explaining now. How it came from the root, from this 3, 2 children will come, from this 2, 2 children will come. Okay, means it will contribute 2 from the level 3. This also will contribute 2 for the level 3. This will contribute 1 for the level 3. Okay. So if you add all of them, you will get this. So it will start in next. See, I'm just doing a naming convention. Okay. I will start from node 0. I will call it children as 2i plus 1 and 2i plus 2. And I will follow this convention throughout the tree. Okay. So it will be numbering, it will assign an additional number to each of the nodes. And this will help me to calculate the width. Okay. So in this case, if you see what is the width, it is 13 minus 7 plus 1. Okay. We'll see that also. Now coming to example 3. Yeah, you can see along the level 0, both leftmost and rightmost not node are same, so it is 0. You can clearly see here. Okay. Coming to level 1, it's as usual. It's so it is 0 means it will be 1 and 2, right? So leftmost node is 1 and rightmost node is 2. And now coming to last node. Okay. So both leftmost and rightmost are same. It will be level. So it is always 0, 1, 2, 3. Okay. So for when I equal 1, if you do 2i plus 1, it will become 3, right? So both leftmost and rightmost are 3. So you have to find out which one is contributing to the maximum width. You can clearly see this particular thing is contributing to the maximum width. Okay. So 2 minus 1 plus 1. Okay. So yeah, friends, that was the tracing. Now coming to the solution. Okay. By default, this is my level. Whenever I am doing a refresh, I will increase the level by 1. You can clearly see here. Whenever from a parent I'm going to a child, I will increase the level by 1. And initially I'm making I as 0 for the root. Okay, because the refresh called on the root. Okay, initially I'm making I equal to 0, right? So when I'm calling the left child, I'm passing the index 2i plus 1. When I'm calling the right child, I'm passing the index 2i plus 2. Okay, this is just additional naming convention. This is just additional numbering to the existing nodes. Okay, this will help me calculate the width. That is the basic idea. Finally, I'm printing my data structure array. Okay, then comes the very important part. Okay, so this is how my data structure will look. The dictionary which I'm using, this is how it will look. Okay, so the can clearly see a dictionary. It will store the leftmost and rightmost Norton nodes. Okay, for every level, see the key is the level here. Okay, key is the level. Any of this level could contribute to the answer. Okay, for each level, I have the leftmost Norton node, I have the rightmost Norton node. They could be the same as well. Okay, so let us see what happens. So as I told, any level could contribute. So first of all, I'm taking the max level. See, most of the cases, the leaf level, that is the max level. See, that only will see maximum is the higher distance, highest distance from the root, right? That is most likely to contribute for the answer. So I'll start from that. I'll take the max level first. Okay, this is a max in number of keys. Okay, for example, see this is at level 0. Similarly, you can see the highest level in example 1 is 2. Okay, so I will start from the second level itself. Okay, what I will do is I will find its width. Okay, width formula is very simple. Okay, the first node, you see a of level of 1 minus a of level of 0 plus 1. Okay, this is my distance. If this is greater than my answer, update my answer. Okay, if this is greater than my answer, just update it with my answer. Okay, and do level of max level is equal to max level minus 1. That means we are traversing through all the levels, including level 0, and we are trying to find the maximum possible width. Okay, whichever has the maximum possible width, that will be updated to answer. Answer is initialized with 0, but it will be updated with the maximum width along all the possible levels. Okay, and finally we are returning the answer. So if you this is because there's a default solution. If you try to find the time and space complexity, so space complexity O of L plus C, where O of number of nodes plus now n of n plus C. Okay, number of nodes plus number of edges, same as the space complexity. And one more thing, we are passing C through each of the levels here. Okay, We are passing through each of the levels once again, and we are trying to see for each level we are doing this operation, and we are trying to find the we are trying to update the answer, because see, we are not sure which on a whole the leaf level, okay, that should be the maximum one. But as we can see in some of the examples, for example in this example, leaf node has only one node, okay, so it's not contributing to the answer. The maximum will come from the level which is above the leaf level, okay, that means this level, one level shorter than the leaf level. So you can clearly see that I've done. So I'm traversing through all the levels, and I'm updating the max level. And if my width is maximum, I'm updating this as well. Okay, max equal to the previous answer maximum or the current width. Okay, whichever is maximum, it will take that. Finally, I'm taking the answer. So yeah, friends, that was all for today. If you have any doubts, please do comment below. See, leaf is, as I told, leaf is my special interest. I believe that I am specialized in leaf. Sorry, tree questions. If you have any doubt, please do comment below. Let us discuss it further. But we have to come with valid doubts. Okay, you will have to discuss your approach, and if possible, please do tell if I can do optimize in any of my answers. Okay, if the optimization possible, please do mention that as well. So yeah, friends, that was all for today. Thanks a lot.